Let us now try to run these models run these regression models and do a hands-on training. We go on our website, and then from our website we click on regression, and under regression analysis we have this under item 3.4 we have the data sets. Let's start first by downloading the housing price data, and I can save this file. It's going to be saved in my download folder, which I know where it is, so I go here. I'll copy it and move it to a more manageable location on my hard drive. So I bring it here and I just paste it from where I need to work it from. And then once I've downloaded and pasted it in a convenient place, then I will go into our commander. I have already have it running, and then I say data, and under data I say load data set. So I say load data set under data. And from there I look for the location, and I know the location, which is right here, and the file is hprice1.rda, and I say open, and the file is open now, and I could see it here. It's the data set is loaded, and it would be good to have the view the data set, let's say. So you could see that the price is in hundreds of thousands, so 300 is actually 300,000. The assessed value of the house is also here, but we won't worry about it. The number of bedrooms are listed here. So the first house has the price $300,000, and the number of bedrooms are 4. The size of the lot is 6,126 square feet. The built area is 2,438 square feet. So that's the total square footage of livable space, but the land size is 6,000 square feet. And then the log transformed variable, the log of price, the log of lot size, the log of square footage. And I also squared the bedrooms, but I'm not going to discuss it today, and the log of rooms. Okay. So I go back here, and you could see that R is now adding the commands automatically. I now would like to see the summary of the data set. So I say statistics, summaries, and active data set, and I click. There are 12 variables. Here's the summary. So the average price is 293,000. The average number of bedrooms are 3.56. The average lot size is 9,000. The average square footage, the livable space, is 2,014 square feet. 69% of the homes are of colonial style, and the log of price and all these are here. Okay. Now the relationship. These are the descriptive statistics. I can also do a graph, a scatter plot matrix, and I click. Notice again. I'll do it again. Graphs, scatter plot matrix. And here I assess bedrooms and price and square footage, and I've pressed Control key to select these variables. And then is there a lot size variable here? Lot size. And I don't need a least square line, and I just need a smooth line, and that's it. And I can click OK, and it should give me a graph, and I just bring it here. And you could see that first of all on the diagonal is the histogram, but here's the number of bedrooms and here's the square footage that you could see. Let's look at price, because that's the variable of interest. You'd see that as the square footage of livable space increases, there's a positive correlation with price. The relationship between lot size and price is sort of interesting. It goes down and then goes up, and then there's an outlier here. There's a very large property which you could exclude from the analysis, because the lot size, there's only one property greater than 20,000 square feet as lot size. So it's a good way. The graphs are a good way of identifying the outliers. If you look at the number of bedrooms, you will see that the number of bedrooms also suggests an upward trend. So good. And the scatter plot matrix was created with this command. Okay. Then we run the regression model, and let's say we want to run the regression model where we say that the price of a house is a function of number of bedrooms. So statistics, fit models, linear model, and the dependent variable is price, and I click on price. So I double click on price, and the price comes automatically here. and then number of bedrooms is the explanatory variable, so I click number of bedrooms and then I click OK, and it will assign the name linear model.1, but let's call it lm.1 rather than linear model 1, so it's a shorter name. So what is the regression model we are estimating? That price is a function of number of bedrooms. Click OK, and here's our model. This is the command that got executed, and here are the results. Look at the R square, R's output. It says the formula we have estimated is price is a function of bedrooms using this data set. It tells us something about the residuals, which we won't worry about right now, and the conditional mean, the intercept is $72,000, and for each additional bedroom the price goes up by $62,000. Look at our t-value. It's greater than 2, and it's statistically significant as well. If you have a statistically significant coefficient, R automatically adds stars, and there are 3 stars here which correspond to almost 100% confidence level. And the adjusted R square is 0.249 or 25%, right? So what is the model telling us? That the conditional mean is $72,000, and then for each additional bedroom the price of the house goes up by $62,000. Okay, now this is good. The next step is to determine what happens if we include the lot size, the land area, into the model. I can go back here, statistics, fit models, linear model, and I have the previous selection here, and then I go in and I select lot size, which is right here. I double click on it, so now it adds it and puts a plus sign in between. I click OK, and look at the new model being estimated. It's right here, and the results are here. Now the 2 explanatory variables are bedrooms and lot size. Now previously, look at the mathematical notation, it has changed, but it's 5.73 raised to power 1 is basically 57.3 or $57,300. Now each additional bedroom will account for $57,300, and the t-value is still higher than 2, statistically significant. And the lot size for each, and it's a variable which is 2.85 10 to the power minus 3 or 0.000285, or and because we have the values in thousands, I can actually interpret it as 2.85. so basically for each additional square footage the price of the property goes up by $2.85, right? So a 100 square foot lot more, a bigger lot would get you $285 more. So 1 square footage equals to 2.85. Now notice that if I look at 1 bedroom house, it's 5.73 or $57,300, and if I have to worry, if I have a 2-bedroom house, the price goes up as well. But what happens when I have the square footage of the built area rather than the lot size? Now basically the model is saying that if the lot size stays the same, that is the land stays the same, each additional bedroom will contribute $57,300 to the price. I will now replace lot size with the built area to explain what all else being equal means. So I remove the lot size and I click on square footage, which is the square footage of the built area, and now you see the values have changed, and this time around number of bedrooms account for only 15.19. It means that if the built area, that is the square footage of the house, does not change, then each additional bedroom will only give you $15,000 more. Now previously we had $57,000 more for each additional bedroom in the last model with the lot size in it, and now we control for the square footage, and then suddenly each additional bedroom is only accounting for $15,000. But the difference is all else being equal. Now you can have a bigger lot and you can add a new bedroom into the property, and that would be increasing the livable space. That was the previous model here. Each additional bedroom would increase the livable space. Now we are controlling for the livable space, and the only way you can add an additional bedroom is by splitting an additional room into 2 and converting that into the bedroom. So basically the new bedroom is not additional livable space but conversion of existing space from some other use into bedrooms. And that where in the scenario where you do not have additional livable space by adding more bedrooms, then the additional bedroom is basically $15,000 versus $57,000 when it results into additional livable space. And the adjusted R square is 62.62 or 62%. So if you look at the principle, in the first model we had each additional bedroom resulting in additional livable space. In that case, each additional bedroom resulted in $57,300 more to your property value. In the second case, when we controlled for the livable space, all else being equal, now additional bedroom that does not result in additional livable space, it's just splitting up a room into 2. Now each additional bedroom results in $15,200. And that is the beauty of regression model, that it allows you to control for other factors. And you see, if you control for the lot size, adding a bedroom means you add more livable space as well, and then you get $57,000. But what if you add a bedroom but you convert some room from a study or from a library or a storage space into a bedroom? Then you realize that each additional bedroom would not get you $57,300 but only $15,200. And that is only possible, these things are only possible to determine if you were to run a regression model. And of course all your t-stats are statistically significant. Notice that we do not look for the statistical significance of the intercept. It's something that we do not worry about in regression for most of the time. Now consider the fact that we have lot size here and we are looking at each additional square footage. You know that the bedrooms may increase by 1 or 2, but the square footage of the property or the built up area, you don't really add 1 square foot of built space. That's just a 1 tile added to your property. So it's good to think in terms of elasticity or percentage change. And again, as I explained, we can log transform the variables and run the model again. I've already log transformed the model variable, so instead of the price variable, I'll replace it with log of price, and log of price would do the trick for me. And in terms of square footage, I replace it with log of square footage and get rid of the square footage variable. And I'm not transforming bedrooms because again I said that you don't increase increase bedrooms by a percentage. You increase it in discrete terms, 1 bedroom versus 2 versus 3. So we leave that as is and run the model again. And our initial looks, we are modeling the log of house sales price as a function of number of bedrooms and the square footage of the built space. You would notice that the log of square footage tells us that for a 1% increase in the built area, the price of property increases by 0.8%, or a 10% increase in the built up space increases the price by 8%. Right? You just multiply this coefficient by 10 and it gets you 8%. The number of bedrooms is 0.03. You have to multiply it by 100. Remember the functional form slide. If I multiply 0.038 by 100, I get 3.8. So for each additional bedroom, I get a 3.8% increase in the price of the property. Right? And if I were to repeat this experiment with the lot size, rather than the log of square footage, I replace it by the log of lot size. Now the number of bedrooms is 0.14. It tells us that for each additional bedroom would give us 14% higher value, all else being equal, or the lot size being equal. And for each square footage increase in the lot size, the price of the property goes up by 24%. Notice that the R square with the lot size as an explanatory variable is 38%, and when the built up area is used as the as an explanatory variable, the model fit is 55%. So it's comparable. No, the model fit is much better with the built up area rather than the lot size. I will now add the variable colonial to the model to see what impact colonial have on the price, and it's a binary variable, 1 0. I'm not going to transform it, and the dependent variable is log of price, so I say OK. And most of the model stays the same. except that Colonial seems to add 3.2%. This is 0.032 times 100, 3.2% to the property value. But notice that the t-value is less than 2, so it's not statistically different from 0, and hence we would not read too much into it. And we believe that the price of a property is not influenced by the type of construction, colonial or otherwise, in this model. And that's one way of doing it. Another way of looking at it is, if we, now here we're saying that the number of bedrooms increases by 1. What if we were to say, what is the distinct increase in the price of the property, or change in the price of the property, if bedrooms is not used as a continuous variable but a discrete or categorical variable? And it's very simple in R. You can actually put parentheses around bedrooms and call it as factor variable, and this time around it will tell us the distinct change resulting from 2, 3, 4, 5 or more bedrooms. So I say okay, and see the difference here. There's probably no 1-bedroom home, and there's only, so the base case is 2-bedroom, and it tells us here with these dummies for 3 bedrooms, 4 bedrooms, 5 bedrooms, 6 and 7, the percentage change in the price compared to 2-bedroom home, and the only statistically significant result is for 5-bedroom home, and it tells us that the 5-bedroom home is 61% higher in price than a 2-bedroom home. So you can do the same with the consumption data, download it from the website, and then there's also a handout that I've made available on how to model consumption data, and then you look at the relationship between households' consumption of food and using the explanatory variables as income, what is the impact of income on food consumption, household size, and then you can break down the household size as adults or children, and you can also compare the household consumption on food with another variable such as transportation, and see how transport spending differ by the number of children and adults. I will now present briefly some of the models that I've seen in a book called Introductory Econometrics by Jeffrey Wooldridge, and I've presented them here just to for discussion. This is a data set of large firms and their salary earned by the CEOs or the chief executive officers. So I'll just read it up from here and show you. In this case, an ordinary least square regression, a simple regression, was fit to the number of, and there were 209 observations. The model is a very poor fit, 0.01 or 1%. And what they wanted to see is how much variation in the salary earned by the chief executive is explained by the return on equity. That is the performance of the firm. Does it affect the chief executive's salary? And the answer is not so much. The R square is only 1.3%, and so the firm's return on equity explains only 1.3% variation in the salary earned by the 209 CEOs. And what it means is that almost 99% of the salary variation is left unexplained from this model. So this is one such thing as very poor fit. So 1.3% fit is not something that you can work with. Then there's another data set in which the salary of a CEO is explained by the sales, the total sales made by a firm, and the variables are log transformed, both sales and the salary variable. The salary variable is a dependent variable. This is a dependent variable. This is the explanatory variable. U stands for the error. And the beta one would then be the elasticity of salary with respect to sales. You know, percentage change in salary resulting from a percentage change in sales. And the reason it is like this is because it's a simple regression model, but we have log transformed the variables. So Y, the dependent variable, is the log of salary, and the explanatory variable or the independent variable is X, which is the log of sales. Okay, so log of salary is equal to beta naught 4.82 plus 0.257 log of sales. What does it mean? It means that for same 209 observations, we get a R-square of 21%, so it's a better fit. And it tells us that that a 1% increase in firm sales increases the salary by 0.257%, which is again the interpretation of inelasticity. So a 10% increase in sales would result in a 2.5% increase in a CEO's salary. And again, it's a better fit, 21% fit. And the model explains 21% variation in salaries as a result of sales. Here's another variable where we are modeling the hourly wage as a function of education. We have observation of 526 individuals, and our R squared is 0.186 or 18.6%. And the education is look at the dependent variable, which is log of wage, and the education in years is basically in the level case. It's not in log transformed, but it has a percentage interpretation if we multiply it by 100. So the wage, if I multiply 0.08 by 100, then I get 8.3, and it means that the wage increases by 8.3% for every additional year of education. So if someone stays in university or school for one more year, based on this data set from this particular sample, their hourly wage would increase by 8.3%. So for every additional year of education, you get 8.3% higher in wage, and this is called the return to another year of education. This is how you compute it. Let's look at another example where we say that the college GPA, that is the GPA earned, that is a grade earned in college, is a function of this variable HS GPA, which is the high school GPA. So basically we're saying what is the performance of a student in a university or college, how much of it is defined by their performance at the high school level, and then also what they scored in some test which is called the ACTs. We see that these two explanatory variables explain 17.6% of the variation in college GPA, and if you look at it further, you see that for a 1 unit increase in the high school GPA, the college GPA goes up by 0.453. So the high school education, basically the quality of high school education contributes to a student's college performance. And I would highlight the last sentence. If the high school performance and performance in the entry exam, which is ACT, explained all the variation in college GPA, then it would have meant that performance in college would be preordained by high school performance. So this low R square is actually telling you that only 17% of the college performance could be explained by a student's before college preparation. The rest of it, that is more than 83% of it, is explained by what they do at college. Here's another example of hourly wage, where we have the log of wage as a dependent variable, education and number of years in education as an explanatory variable, the number of years of experience, and tenure, meaning some sort of job security. So you look at this model, and it's a very interesting model. First of all, it has it explains 32% variance in the job, in the wage, in the log of wage, that is, and it's a good fit. And we have standard errors reported here. And basically, if you take the coefficient and divide it by its standard errors, it gives you the t-value, the t-test that you see. And you look at it, and you want to see what is the impact of return on experience controlling for education and tenure as constant. So what happens if the education and the tenure is the same? How much more would you earn as a function of your experience? And obviously the null hypothesis is that the experience would have no impact, and the alternative hypothesis is that no, experience should have an impact and should return into higher wages, and the null hypothesis is rejected here because you have a very you have a good fit here, and the critical value for 5% value is 1.65, 1.64, and the t value here for experience is 0.0041, the estimated coefficient, divided by the standard error 0.0017, gives you a value of 2, which is, again, as I mentioned, for a one tail it's 1.64, for a two tail it's 1.96, and in both cases 2.41 is greater than these numbers. So you can say that yes, experience is statistically significant at the 1% level, and that experience is greater than 0 at the 1% level. So basically it means that if you hold tenure and education constants or fixed, adding 3 more years increase in experience increases your wage by, let's say, 0.0123. So wage is only about 1.2% higher for someone with 3 more years of experience, provided their education and tenure is fixed. We can do the same for education by holding experience and tenure constant. So if experience and tenure are held constant, and let me switch to pen here, then what would be the impact of 1 more year of education? Well, in that case, if the experience and education are held constant, 1 more year of education would mean 0.092 times 1, which is again 0.092, but then you have to multiply it by 100, and that gives you 9.2%. So all else being equal, 1 more year of education let me write it here. 1 more year of education results in (9.2%) more wage. So compared to experience in this data set, education results in higher wages. So basically telling you that experience is not resulting in much higher wages, as much increase in wage as the education does. Lastly, we are looking at the impact of various variables on the price of house. And in this case, we are looking at some negative externalities. So NOxes are the nitrogen oxides, and so we're looking at the pollution level near the property, and distance is the distance from some employment centers. And we are looking at if the increase in distance between the property and employment center, what would be the impact of that. We're also looking at the impact of number of bedrooms, and then there's this thing called student-teacher ratio. Basically, higher student-teacher ratio means that there are more students per teacher in a neighborhood, which is not good, and therefore it may have an adverse impact on property values. So the dependent variable is log transformed, and the distance and NOxes are log transformed. So basically we are looking at the model. It tells us that for a percentage increase in pollution, NOxes, the price of property goes down by 0.95%. So if this goes up by 10%, the price of property, if the pollution increases by 10%, the price of property goes down by 9.5%, right? So I just multiplied this with 10. If the house is located a percentage increase in distance between employment center and the property, and the price of the property goes down by 0.13%. So it makes sense to buy property closer to employment centers. One additional room would result in 25.5% increase in property, multiplied by 100. Remember that. So basically the price is very sensitive to the number of bedrooms. Each additional bedroom accounts for 25.5% increase in property value. And again, as the student-teacher ratio increases, the price of the property goes down. And if the student-teacher ratio increases by 10, the price of property goes down by 5.2%. It goes down. So I multiply 0.05 by 10 to get 5.2% for a 10% increase in student ratio. So it tells you that the housing prices are sensitive to student-teacher ratios. There's another model again. I thought that the previous one was the last one. Again, we have the log of price. The price variable is log transformed. The square footage is of the property is in log format. Number of bedrooms is also is not in log transform, and number of bathrooms are in also not log transformed. You would notice that the model is telling you that each additional bathroom results in higher property value, but each additional bedroom results in negative or lower property value. So a bigger number of bedrooms would have lower property value. And this is something called multi-collinearity. And at this stage of the game in statistical analysis, we will not discuss multi-collinearity, but because there are two very collinear variables, the number of bathrooms and number of bedrooms in the same model, one of the variables would take counterintuitive sign, which is the case here, because you would assume that higher number of bedrooms result in higher property values, which obviously is not the case here. The model fit is 80.6%, which is a very good model fit, but again there are 19 observations, so it's not really large data set to have any confidence. So this basically concludes our presentation on regression models. The best way to learn regression model is by doing it. You can actually open other data sets. For example, if I click here, data, and say data in packages, and read data set from packages, and I can, let's say, click on car, and this is a package, and look for data sets. And you can read about this. There are help files available on all of these. Let's say there is a dataset called Ambrose, and I can see if there's a help. I clicked on help, and there's help on this dataset available, and you can actually then upload that dataset, and then I can say, okay, I want to use this dataset. Now this dataset is open. You can view the dataset, and you can have a dataset on labor force participation for women, and you could see how women labor force participation changes by having children and the age of children. So this is just one small example. There are tons of data sets that are shipped with R that are already there. The way to find them is to click on data and then say data in packages, and then read data from an attached package, and then you can actually look at these data sets and work with them. The more you practice, the more you will find confidence in your ability to run regression models and make some interesting conclusions from there. So I wish you luck with your future research, and this concludes our presentation on regression models.